All right. Hi from me too. Good to see you all. Maybe again on the highest university of Germany. I'm working at Ulm University, and we also have, like, unofficially the highest tram station of Germany. But I think that's just because nobody else has bothered to check if their tram station is actually higher than ours. So there's an unofficial, like, A4 paper hanging at the station that just says, yeah, highest tram station in Germany. Yeah, thanks for the introduction, David. I'll be talking a bit about synchronization. We already talked about concurrency and async code, and now we will look at how to synchronize access to shared data structures or shared variables, shared segments of memory. If you want to follow along, I also uploaded these slides already. Maybe a short anecdote on that. At last year's Sigtoberfest, I also gave a talk, and for that, I registered sigtoberfest.fun for a single year. And of course, I forgot to cancel it. And now I've got sigtoberfest.fun for another year. So, so that I don't have just wasted my money, please go to sigtoberfest.fun, and there you will find the slides and can follow along if you want to. Great. So far so good. For a little motivation, who of you has already cooked with someone else together? Yeah, that's most of you. And I've also done that quite a few times. Me and a friend group of mine, we do this regularly. And I hope that they don't watch the stream or watch the YouTube video, because I actually hate it. It's always like a too small of a space, and there's only one stove or only one pan, and then 4 or 5 people have to work on the same pan and on the same stove, and it always gets confusing. And uh, then one person is cutting the tomato wrong, and another one is doing whatever. So I don't enjoy this as much. I do like cooking in general, but I try to keep it for myself. Sure. I said you need to coordinate access to the shared resource, which is in our case the pan or the stove. And this is obviously the same with programming. There we don't have pans or stoves, but we do have shared memory or shared resources that need to be coordinated between threads, so there can be safe access on them. And this is what we will look at today. So just to get started, a little programming example. This is a incomplete stack implementation where, let me get that pointer, where we have a backing data structure which I just chose an array list for, and I implemented the push operation. And traditionally, this would just be self.backing.append and then the value. But in order to see what's going on, I wrote down 3 lines more, which probably is what append is implemented with. So we will start by getting the length of our current data structure, so all items, and we modified the last 3 slot in our data structure, and then we increment the length by 1, and with that our push operation succeeded. So if we now look at how 2 different threads could access that, I have a blue and a green pointer for that. The first one gets the length, then gets the new value, and then just gets descheduled for whatever reason. Now the second thread appears, also gets the length, and now gets the value too, but since our first thread, the blue one, didn't update the length already, the green thread now just overrides what the blue thread said in the first place. And then green just continues updating the length, and after that blue continues also updating the length. But in the end, what blue did just didn't have any effect because, as I said, green overrode it. This obviously is bad, and so we need a way to notify blue and say, hey, please stop. There's another thread currently accessing this resource. You need to continue later. And that's exactly what locks are for. For this example, I chose the possibly easiest lock out there, the mutex. And with just 3 added lines, so the declaration up here and then a lock and an unlock, this unlock would typically be implemented within a defer block, but to make it more visible when it appears or when it's evaluated or run, I put it explicitly at the last statement. So now again, we have our blue and our green thread. The blue starts by acquiring this lock. So blue now has the permission to continue, gets the length, sets the item, and now gets descheduled again, and green appears, also tries to acquire the lock, but since blue is already in the critical segment of our code, this is where bad stuff can happen. Green cannot acquire the lock again and also gets descheduled, and blue can continue updating the length. And then as blue is now outside of the critical segment, it can unlock the lock again, which leads to green being able to continue and running through our lines just regularly. And now green did not override what blue said initially, and we pushed 2 elements to the stack, and we can all be happy. So this is what locks for. It solved our initial problem. But as I said, we used the most simple one, the mutex. There are obviously different solutions for more complex synchronization problems or locking problems. Just to point out a few, there are, for example, semaphores, which with which a thread can also acquire like multiple locks, so the semaphore can be locked multiple times, if that makes sense. There are non-blocking locks, which is often called try-lock, which does not block the thread, but just returns false in the case that it can't be acquired. There are also read-write locks to differentiate between read operations and write operations, where multiple read operations can occur concurrently, but if a write operation occurs, then also read operations have to be blocked. There are also reentrant locks. I think in Zig they are called, or the mutex variant that is reentrant is called recursive mutex, because a thread can then acquire the lock multiple times, which would not work with the standard mutex implementation. There are also phases or barriers and so many more stuff. So as I said, with different problems, you have to choose the right tools. And what we want to look at today, if locks are even the right tool at all. So there are different solutions, and this is what we will investigate, because locks do have hidden costs. It's not just, I throw a mutex on there and everything's fine. That might be often the case, but it does not need to be the case all of the time. So there are hidden challenges or hidden costs associated with that. For example, there can be bottlenecks. So if multiple, or if we have like many threads trying to acquire the same lock, then all but typically one thread needs to get descheduled and only one can do work. And this just takes sometimes much time before then all other threads can proceed. There are more failure modes, which we will get into detail in, I think, a few animations. And it's easy to just think that we solved the problem by adding a lock, but in practice, as I said, there might be implications which we are then not thinking about anymore. Because it does look simple, doesn't it? Just putting on lock and then unlock and then you're finished. But yeah, that doesn't need to be the case. So flashbang, I said we will look at a few additional failure modes that locks can introduce in our code base. There can be problems with contention. So contention is, as I said, when many threads do want to acquire the same lock, and this will just won't work, and then all but one thread needs to be descheduled. And this just introduces performance degradation, as just one party can continue with the work and all others have to wait. We can also capture this in a more theoretical way. So you might know from school or university or wherever you have learned computer science stuff that this seems backwards. That we can like calculate the speed improvement by introducing concurrency in our program, and there's Amdahl's law for that. I'll just quickly sketch it out. You cannot read this, can't you? But is this the fault of the chalk? Maybe if I try something with more contrast, like red. Nah, that's also probably not readable. Whatever. And I'm not using the board. So in Amdahl's law, it's roughly like 1/1 minus the time that can be parallelized, and so on. And since the time that can be parallel, or that the time or the portion of the code that cannot be parallelized is like in the bottom. If it gets bigger, then Amdahl's law leads to a smaller value, so a lesser speed up, if that makes sense. So if more of our code has to wait until another part of our code is finished, then we obviously gain less speed up from our concurrency. And that's bad. If we do implement concurrency, then we want to gain as much as possible from it. Then there's starvation. That's kind of similar. I just skip over that for time reasons. Priority inversion is pretty interesting because that's often unnoted. This is when we have, for example, 3 threads. One has a low priority, the other one has a medium priority, and the third one has a high priority. The thread with the lowest priority acquires the lock, then gets descheduled for whatever reason. Next, the thread that has the high priority does want to acquire the lock, but cannot do so as the lower priority thread has already done so, and gets also descheduled because it has to wait. And now the medium thread gets run and preempts the lower priority thread as it has a higher priority. And H, or the high priority thread, has to wait indefinitely because L just doesn't get scheduled anymore because it has a lower priority than the medium thread. That's priority inversion. And as I said, that often gets is unnoted because it's a bit hidden from us. Lastly, composability. Composability is when a function that how do I say that? Or a function that does acquire a lock is, or it's rarely a good idea to call that function from within a critical section. And this again leads to just more coarse-grained locks. So we are incentivized to lock a larger critical section, which in turn just makes all those problems even worse. And long story, short summary, are locks good? Maybe, maybe not. We will look at an alternative. This is lock-free programming, so locking without locks, synchronizing without locks. We already looked at the first part. The rest of my talk will be more of a theoretical perspective, or how this whole concept of lock-free programming works. Then we will look at how this can be implemented in SIG. And lastly, if it is a good solution, so for internationals here, this is the German eierlegende Wollmilchsau, which is a jack of all trades. And we will look at if lock-free programming is also a eierlegende Wollmilchsau of programming. Okay, so how can we get rid of locks? The problem is our critical section. Because this needs to be guarded, this needs to be locked. So now if our critical section could be so small, so tiny, that there's just no possibility for any other thread to get in there while we are executing this section, then we would be fine. Then there would be no need for locking, as there's no possibility for other threads to get in there. And this is in theory, atomic operations just do provide this this attribute, because we say they are invisible, so they do work successfully or they don't work at all. but you cannot like observe any intermediate result of atomic operations. This is what makes them atomic. For example, there are atomic loads or atomic stores, stuff like that. And the atomic operation that's most important for us is called compare and swap, or in short, CAS. I don't know if anyone ever has said that, or it's CHS, CAS. This is the workhorse of log-free programming, and I have noted down, like it looks like ZIG, but isn't completely syntactical correct, but it serves the purpose. So we always, or I use the pointer here, we always get a pointer to any data, we get an expected value, and we get a new value. And our goal is to set the pointer to the new value, and then we return if it succeeded or not. Often, and that's also the case with ZIG, there is no bool that is returned, but the old value itself, and if it didn't succeed, it's just null. But writing bool was a bit simpler. So the first step of our compare and swap operation is checking if the value of our pointer currently is the expected value. If that's not the case, then somebody has modified something, and we aren't at the state we expected to be at. So we just abort and say false. We have to try later. But if it is the expected value, then we can just set the pointer to our new value and return true at the end. So we can say like, look at this memory address. If it still contains the value I expect, then and only then, and this is the important part, update it to the new value. This is like when I need a spontaneous meeting with my colleagues, I just pop my head into their room and I'm like, do you have time currently? And if they say no, then we are kind of here, and I abort and say, okay, then I try later. And if they say yes, then I have a spontaneous meeting with them and I return true, and then I'm happier. So this is the working horse, the compare and swap operation. And while this does look like a lot of code, we will see later that it is indeed an atomic operation and that it results in just one line. Great. So now we can compose this single operation to a whole loop. So this is the compare and swap loop. This is what powers most of the log-free data structures. And this matches the little meeting story I just told. So this just indefinitely checks if our compare and swap operation succeeded. If yes, then fine, we can exit the loop. If no, then we update our temporary values and then retry afterwards. We will see this later also in the ZIG example I coded up. Great. And we call this optimistic concurrency because, as I said, we first try and assume that we can set the new value, which is pretty optimistic, and only if it fails, we then try again and are again optimistic, and hope that we do not fail again. Yeah, this often gets wrapped into atomic variables. So we had atomic operations, atomic variables. Just wrap this compare and swap loop so that you have, for example, an atomic integer where you then can set new values or add new values, load values atomically, so on and so forth. Good. The cool thing about this this log-free design is that we can like reason about different properties of it, and there are three important properties that we want to look at a bit in detail. Those are three levels of freeness. They are called, and they describe what guarantees our concurrent data structure has when we access them. So obstruction freedom is the lowest guarantee. This just guarantees that if there are no other threads, or if all other threads are currently suspended and not scheduled, then our current thread can access the data structure and can proceed with its operation. So I tried to model this as a little diagram. So data is our shared resource. Thread is the current thread we're looking at. And other thread is just the rest of the system, or all other threads in our program. So we first try to access data, but since all other threads or any other threads already are accessing our data, we fail and just return a failure is indicated by the dashed line. But then all other threads are being suspended or aren't scheduled anymore. We try to access this shared resource again, and now we succeed because there's just nobody else that blocks it. So this just guarantees progression in isolation and is the weakest guarantee. Next, there's lock freeness. And why this whole paradigm is called lock-free programming doesn't mean that any lock-free algorithm is also lock-free on this slide, which is why lock-free algorithms are also often just called non-blocking algorithms. But that doesn't sound so exciting. Non-blocking sounds kind of bad, so I also call them lock-free algorithm. And when I'm speaking about lock freeness, I typically mean the whole paradigm and not only this attribute, just so we are speaking of the same thing. Yeah, lock freeness is like one step further. Now it's guaranteed that at least one thread always can make progress. So even if there are other threads working on our shared data structures, lock freeness guarantees that at least one of our whole systems makes progress. So it is fine that all other threads are just idling or in the loop forever, but at least our thread on the top does make progress. That is the lock-free attribute. And this is typically guaranteed by our compare and swap loop we saw earlier. So whenever we have a construct like this is typically lock-free, and we can reason about that, because if this compare and swap operation fails, what does that mean here? That means that another thread has successfully changed the state, so another thread's compare and swap operation was successful. So there's always at least one thread making progress. I hope that was understandable. So then the last guarantee, which is the biggest, greatest guarantee, is weight freeness. Weight freeness guarantees that in a finite sequence of steps or number of steps, every thread is guaranteed to make progress. So this wasn't the case with lock freeness. There we can still have a live lock where we just are looping over and over. Weight freeness does provide that guarantee. So our current thread and all other threads are eventually going to make progress. And that's not always trivial to achieve. So there are certain algorithms or certain data structures that let individual threads, for example, reserve a certain spot in memory, which they then can access instantaneously, which would lead to weight freeness. Now the clockwork would come in handy again, but I try to explain it just with words. Also, if you think about a queue where we have a head and a tail pointer, just using this compare and swap algorithm could lead to the tail pointer pointing to the, or could lead to a new element being added, but the tail pointer still points to the element above it, because there are two operations that need to succeed. The addition is one compare and swap, and the update of the tail pointer is one compare and swap. And if this update did not yet succeed for whatever reason, then another thread currently accessing our queue could like help the first thread and set the tail pointer to the new value, and then the original thread who did the push operation on the queue, its compare and swap would be successful in the next try. And this would also lead to weight freeness if different threads help each other to progress. But as I said, that's not trivial for all data structures. We have to explicitly take care of that and explicitly think about that, while log freeness is way easier to achieve with just this typical compare and swap loop. And those three types of guarantees is what makes lock-free programming so cool, because with blocking algorithms, you got none of that. They can do whatever they want, and it's pretty hard to reason about progression guarantees with typical locks. They don't even provide obstruction freedom, at least by default, which lock-free algorithms do. Good. So far, so good. That's it with lock-free coding. So you now hopefully have a at least foundational understanding about what is going on. The gist of it is we have atomic operations like this compare and swap. Their critical section is practically non-existent, so no other thread can observe intermediate values or can go in between operations. They succeed or don't succeed at all. And this is what makes synchronization possible without the need of locks. Good. How can we now implement this in Zig? This is probably what you all have been waiting for. And it's pretty easy, to be honest. Because those atomic operations are just a thing that our modern CPUs support. There are different flavors of those atomic operations. They are called test and set sometimes, or compare and swap, fetch and increment. Compare and swap, I already said. And they all result in slightly different instructions. Those are from the x86 instruction set. You notice that they are all preceded by lock, and then the respective locking or the respective atomic operations. We can also look at this quickly in the compiler explorer, where I provided a short example. I just used compare and swap here, which is abbreviated with the CMP-XCHG for change. We want to swap a 32-bit integer. We want to check this pointer. If it is currently still 0, then we want to change it to 1. And if we look to the right here, then there is our compare and swap operation in the instruction set, which again is the lock operation followed by compare and swap. If we would, for example, have a load or store, then there would still be this lock instruction followed by the load and store. And as I said, this is executed atomically, so no other thread can intervene. Good. So lock-free programming is enabled by the hardware itself. We don't have to build software support for that. We can just translate functions or instructions directly to those lock and compare and swap operations. And Zig just provides built-ins for that. So remember the compare and swap operation I implemented in pseudo-Zig earlier. This is just this built-in. It takes a whole lot of parameters or arguments. So the type of the pointer we want to override, then the pointer itself, the expected value, the new value, and some stuff we will look at later. And you also notice that it again comes in two flavors. This is weak and strong. I think that if you program on modern x86 hardware, there is no difference between them. But with compare and swap weak, the swapping operation can be successful, but the atomic operation, or it is possible that the atomic operation still fails despite really being successful. I think this is only the case on older ARM instruction sets, so don't worry about that. I typically use the weak flavor, firstly, as I said, because it doesn't matter. And we also, with this compare and swap loop, we natively implement the retry that the strong version would provide us. So I just opt with the simpler one. But as I said, don't worry about it if you're programming for modern hardware. This shouldn't be too different. Good. So in our Zig code, we can just use one of those built-ins and be happy as they would be directly translated to what we saw earlier in the compiler explorer. Then from this built-in, we can now build atomic variables again, just like we did earlier in the pseudo-Zig version. Zig already provides std.atomic, which contains an atomic value, which, for example, has, first of all, an init function where you can set the initial value, and then fetch and add would be getting the current value and adding the first argument to it, so we would just increment it. Those two lines would exactly translate to just this single built-in, which is atomic read and write, with the operation here and the value here, but working with like a real type and a function-looking thing is way nicer than always writing out this old beast. Right. And we again see there's another additional parameter, just like we had here earlier. This is like the same type, and we will get to know it in a few slides. Good. Good. So now the first real working Zig example. I implemented a stack in a log-free way. This is like the classical example you also teach students. It's called the Treiber stack. The original paper called it that way. And for now, I implemented the push operation. So first, we start by allocating a new node, initializing the new node with the provided value, and its next pointer is, for now at least, null. And then we start by our compare and swap loop we already saw earlier. We use the atomic load operation to access our current head. So again, this has to be atomic, so nobody else can like intercept our load. We then set the next pointer of our new head to the current head, and then we try to exchange the current top of our data structure with our new head, but we only do so if the current top is still the top that we recorded here. So this makes sure that in this line, or in between this and that line, nobody else modified our concurrent stack. And if that would be the case, then this check would be false, and we would just rerun the loop again, getting old head, setting the pointer again to the now updated head, and trying to exchange the pointer again. So now a question for you. I said the top needs to be loaded atomically, and we also use an atomic instruction here. But why doesn't need, or why is next not atomic? So shouldn't this also here be an atomic value that we only modify atomically? Any idea on why I implemented it how I did? Yeah. Oh, I didn't quite understand that.
The water pattern water water. You had the people.
Yeah, exactly. So next isn't shared currently. Next just exists on this new memory space we just allocated, but nobody besides we currently can access this memory. So next does not need to be synchronized in any way. We can just access it directly. While, of course, top can be accessed from other threads, which is why we need to interact with it in an atomic way. Good catch. Just for completeness, I also implemented pop, which looks pretty much the same. We also have our compare and swap loop now directly here. We atomically load our current head. We temporarily store the next, so the second element in our stack, and then we try to swap our current top with the next element we just recorded here. but only if it didn't change, so only if it still has the old value. If this is true, then we exit the loop down here after deallocating the old head. But if it's false, then we just rerun the whole loop again and try another time. Remember, optimistic concurrency. Good. All right, so now let's look at why we need those release and acquire, and we also had acquire and release and acquire here. So why do we need those two atomic order arguments? I also prepared a little intro example for that. So imagine this is executed by thread 1. This is executed by thread 2, while both can access the data variable. I know, again, not completely syntactically correct, but it's for the purpose. While for us, this looks, or at least at first glance, this looks completely fine and completely normal. We set data, then set data ready. So now this loop can exit and use the data. This can lead to severe problems because no, it doesn't look right. The compiler as well as the CPU itself can and will probably just reorder those statements. Because while we clearly see a dependency between this data and this data ready, the compiler and the CPU probably won't see this dependency as it is not explicitly encoded in our program. So this use data could probably move before this while loop to, I don't know, for example, mask the access time or the load time that data needs or whatever, and then our program will already be faulty. And this is what we obviously want to prevent with log-free programming. As you can imagine, if we go back and look at the ZIG code, if, I don't know, the load and the compare and swap instructions are interchanged or moved around, then it just doesn't make sense anymore. We are loading and comparing values that aren't current anymore, and we need to prevent this. And therefore, we do have those two additional parameters. So there are different modes that we can order instructions. So those parameters prevent certain reorderings. And for different cases, we want to allow reorderings, and for others, we do not. So there are different ordering properties or modes that we can specify. I am going into detail on 3, but there are, I think, 2 more. So there is unordered, which doesn't really provide any guarantees. I think the Java virtual machine uses that for its shared variables. There's also monotonic, which just makes sure that operations on the same memory address are always in a predefined order, but doesn't guarantee like accesses to different memory addresses. But we will look at acquire and release and acquire release. And now I already spoiled everything, but those are the 3 main ones or most important ones, and those are also the 3 that power the log-free stack that I am. While I am a bit proud of this visualization because I think it looks pretty nice, it doesn't really fulfill the purpose of explaining everything very good, which I unfortunately only noticed today while driving here to Munich, so there wasn't really time in redoing everything. So I'll again try to explain it briefly, and we will also again look at the example, but just to make it short. So acquire is typically used when we want to access variables. So every time we load or we read memory locations, we use the acquire. This can be thought of like getting a log where we enter a section that we do want to make sure that everything that happens before it, we already captured in our read. and we cannot move anything after the read. Release is the exact opposite. It's mostly used on store or write operations and can be thought of like an unlocking of a lock, where everything after should be kept after it and not moved up in our critical section. This is why the barrier is here, and like this can't pass it downwards, and here we cannot pass it upwards. Acquire and release are also combinable, where we just introduce two barriers where we can't move up and down. This is, for example, useful for this atomic integer thing I showed earlier, where we had this fetch add operation, as this does a load and a write, both in one atomic operation. It would also acquire and release at the same time, so therefore this acquire release guarantee is there. There's another one that's even that provides even more guarantees. This would be called sequential consistency, which works pretty much like acquire release. So there are also two barriers which we can't cross in both directions. But sequential consistency would also make sure that atomic operations always occur in the same order. So even if we would have multiple operations in here, they would always have a deterministic order to them. You typically use the sequential consistency when you don't have any idea what you should do, as this just makes sure that everything works like intended, but obviously comes with a performance hit, as the CPU can not optimize your stuff better. So if you then quickly go back to one of the Zig examples, maybe the push. So we had two atomic operations here. There was the load and the compare and swap. Load uses acquire because I said load operations typically use acquire, because we want to make sure that our compare and swap here always uses the most current top that's loaded there. Because where's the slide again? Here with acquire, any memory operation down here cannot move up through the barrier, and this way we always load the most current one. So compare and swap could not move before the load and access a outdated variable. And then we have compare and swap itself. We there use release and acquire. So release would be used in a successful case. So if we successfully compare and swap the value, we set a release barrier. If we unsuccessfully compare and swap, so we have to try again, we again use acquire. This is because we don't want this load to be moved before the unsuccessful case, so that we in the next iteration again have the most current version of the loaded value up here. And oops, what have I pressed? And the release in the successful condition is used because we also want to signal to other threads that now we are finished. The top pointer did get updated successfully, so other threads then do have access to the most current value again, as they cannot pass this barrier upwards. This is roughly how those three guarantees work. But as I said, it's pretty complex in practice, and if you're unsure, just throw sequential consistency on there and it will work just fine. Good. Until now, we only have talked about like the upsides of log-free programming. We don't have problems with contention, for example. We don't have deadlocks. We can have live logs, but if we are careful with our implementation, then we can implement it in a log-free way, which then gets rid of live logs. So I just mentioned good things about log-freeness. But indeed, nothing is perfect, and if log-free programming was perfect, then why would we have logs anyway? A pretty common example or a common problem that we can encounter with log-free programming is the ABA problem. And to make it less technical and have a little fun example, I generated 3 images of a person that's waiting in front of a red light. So this is the first state, that the person observes the traffic light is currently red, so it's blocked. It cannot progress. All right. Then, I don't know, some time passes. The light is red for a long time. The person falls asleep. But while it falls asleep, while it is descheduled, the light now is turning green, but without the person in the car noticing it. And then after they wake up again, the light again turns red, which they notice again. But for the person in the car, this state and this state is not distinguishable got it, from each other. They do not know that the light did turn green in the meantime. So if you now try to translate this to our stack example, we can think of like a thread wanting to pop the top element. Maybe I go back to the code. Here. So thread A wants to pop the top element. It executes this function. But now, for whatever reason, before we try to execute compare and change for the first time, the thread A gets descheduled because thread B arrives, and thread B pops. I would have loved to use the board for that. Thread B pops 2 values, and so they pop. Let me try something. Oops. Okay, I try to explain it with text. So we have A and B and C. Now, thread A has stored the, so A is top, and thread A stored the top so that it can access A.next, which is V later, to then set the top pointer to B again. Good. Now thread B arrives and pops A, pops B, while thread A is still suspended and not doing anything. And then thread B pops our A again. And this does not have to be logically the same A again. The only thing that's relevant for our compare and swap operation is that this pointer has the same value. And if you, I don't know, for example, use any allocator that reuses memory, it can be possible that another allocation for another node will eventually be in the same spot that our thread A remembered. So now we have the problem that thread B is finished. Our stack looks now like this, and thread A tries to continue. So thread A remembered this address. This address, for whatever reason, now matches or we can also call this A prime, matches the address of our current top. So for thread A, it looks like, or for the compare and change operation, it looks like it looks like this situation looks like for our person. They observe the red light, but they do not know that something changed while they were suspended. I think in the stack example, this isn't such a huge problem, but this can have semantic issues because as the state changes and the thread doesn't notice it, it will act like the state didn't change, which can easily lead to corruption, especially if we are dealing with pointers. So keep this ABA problem in mind. There's also not a cookbook recipe to avoid this ABA problem, so you have to evaluate and think on a per case by case basis how to avoid that. But 3 pretty common ways to avoid it are, for example, using tagged pointers. I would guess most systems are 8-bit aligned. This would mean that there are at least 3 bits that are always 0 in a pointer value, which we can, for example, use to, I have slides for that. So this is the middle part. We can use those 3 bits to, for example, store a version number. And then every time any compare and swap operation succeeds, we just update this version number and compare it in thread A's compare and swap operation. And then even if the address didn't change, the tag or version number in the pointer did change, which would be noticed by the compare and swap operation, and it wouldn't succeed. This is also possible without pointer tagging, so there exists a double compare and swap operation, but I don't think that's the case for x86. I think it's only in the ARM instruction set, but there you can explicitly like pass 2 pointers, which our original pointer, the expected value and the actual value, and now a version pointer, a expected version and an actual version, which does those 2 compare and swaps atomically. But as I said, I don't think that this operation is present in x86, which is why pointer tagging exists. Another solution might be hazard pointers, but as I'm already 5 minutes over time, I'm going to skip that. Great. So now that you also have learned about a few downsides of log-free programming, so mainly this ABA problem, we can finally think about if log-free programming really is the eierlegende Wollmilchsau or the jack of all trades of synchronization. So to remember, when are logs good enough? Logs obviously are pretty simple. So when performance is not that critical, or there are only a few threads accessing a shared resource for a few times, just throw a mutex on there and it's fine. It's probably easier to understand for such simple cases than using a compare and change loop. Also, I said in the beginning that there are not only mutexes and that kind of stuff, but there also exist barriers and phases which are not only used for concurrent access, but which can also coordinate threads in general. So if you want to make sure that, 10 threads like stop at one coordinated point, and only if every thread access or rise at this point, then they can continue together. This would be a prime example for using logs. So I'm unsure if the Zig standard library implements such haste logs, but those aren't too hard to implement by yourself. This wouldn't really be possible with log-free programming. But on the other hand, when is log-free programming actually good? So it typically has better performance, especially under oversubscription of threads. So if there are way more threads than there are CPU cores, the scheduler has to block some threads, and if it blocks threads that currently have a lock or acquired a lock, this just makes things take even longer, since those threads cannot release the lock and have to be rescheduled again to release it. This is where log-free programming really shines. It also is not susceptible to this priority inversion, which is pretty tough sometimes to notice and fix. And also not susceptible to deadlocks or null live locks, maybe, but can be easily avoided. And especially we don't have any dumb delays because of descheduling, as we do not have to wait. We can just try again, and that might be enough to then succeed. Great. That's not quite it. TLDR logs have real often hidden problems. Non-blocking algorithms basically just use atomic operations, mainly this compare and swap, but also atomic load and store are really important things there. Compare and swap inside a loop is the main building block of different data structures. And while they do have nice properties like those freedom guarantees we saw earlier, they do also have problems. What doesn't have problems? So if I would put one statement under this talk, it would be: don't be afraid to use logs, but also do not limit yourself to them. There are real use cases out there where such high performance is required and low latency especially is required, that also in practice sometimes log-free programming is used. I know of at least one banking software provider that implemented their own insanely huge log-free implementations of a shared queue, which is pretty funny because it's written in Java. Who the fuck uses Java to implement performance-critical applications? But it's really cool to see this in practice and to see how much throughput you can achieve with this kind of implementation. So thanks for attending. Thanks for listening. I hope that the technical parts didn't scare you off and you at least got the gist of it. And now you're free to ask questions.
Yes. So thank you, Lukas. This time, as it will, we will use a microphone for the questions. Okay, thank you.
Question up there, so you have to walk over there. Is
Yeah, so thank you for the great talk. It was really, really great seeing you explain such hard topics in such a simple way. When I think back 20 years ago, when I played with spin locks and all that stuff, I think I read that when you use the locked instructions on x86, that they basically pause the cache line synchronization between the cores. And so when you heavily or aggressively spin in your while loops, you basically don't you produce side effects on other cores?
ooh, that's pretty technical. I'm not totally sure, or I haven't thought about that. But you said that cache lines do get discarded with the lock instruction. Did I get that right? Uh-huh.
Yeah. Uh, uh, mm, mm.
Yeah, that could be the case, but I'm not 100% sure about that. Did you all get the question? I'm not sure. Okay. Otherwise, I could have repeated it.
More questions.
Hey, thank you. That was really nice. I want to ask you a question about your slide where you were discussing acquire semantics with the compare and swap. The one with, yeah, so the one with the code.
Yeah.
So you mentioned that the load should have, this one, thank you. This one, the load should have acquire semantics so that the compare exchange cannot be reordered above the load.
Yes.
But doesn't the compare exchange have a data dependency on old head, preventing that from happening?
Yeah, that's also true.
But so then my question then is, does it matter to use acquire? Can you then downgrade to a weaker one?
Well, we would need to test that, but by just looking at it, yeah, it could be also fine to use monotonic.
Okay.
And to gain, I don't know, one cycle of performance improvement. But
Yes. Yeah. Okay, thank you. That was helpful.
Maybe one more question before we go into the break. Yes.
I think if you speak loud enough, it might also be picked up by my mic.
Is it possible to reallocation? Is it possible to do reallocation in a weight-free way? Because when I was playing around with weight-free or log-free or whatever data structures, I was unable to do it.
Just let me quickly pull up the slide with the different freedoms. I don't find it. So the question was if it's possible to implement allocations in a weighted way. Reallocation. I also have not thought about that. So you said that you once experimented with that? And yeah, I need to pass on that. I'm sorry. Right? I also have a question. Why the fuck isn't this working? Did you have lectures in this hall? Am I just using the thought wrong? I mean, you can't see really anything when I'm writing there. My and I had like 10 examples that I would have used the board for. Well, you know what you have to check next year.
So again, thank you, Lukas, for your report.